Good day everyone and welcome back to our session of linear regression. Yesterday we had discussed about the overview and some of the interpretation of the outcome of linear regression. We had covered up to the multicollinearity, and today we'll just recap quickly and we'll go back to the model and we'll see how a linear regression model is built from the beginning, how we do this, what steps we follow, and what is the end. So first thing, we must discuss the assumptions which we did yesterday. The independence of observations, it's the autocorrelation. Variables, a predictor should be independent. Data should be normally distributed. Equation should have a linear relationship. And homogeneity or variance or the residual, which is also called errors, which we normally check for the residual after building the model. Let's take this data set with 1124 rows and 7 columns, which we saw yesterday. This is the data set we were working on. And overall service level is the dependent variable. These 4 are predictors. We also have 2 factors, or 2 categorical variables, which is the team leader and years. We will work on R and we'll go step by step. We'll also look at some of the libraries. Once again, I say the objective is not to teach you R over here. The objective is to teach you the concept and the steps of a linear regression analysis. What we do once we have the data set, we get into the exploratory data analysis, which is the EDA, and we look at the structure quickly. When we look at the structure, the objective is to see the types of data we have. So it clearly shows we have 2 factors and 5 continuous data, which is numeric. Let's move to the next step. Before we get into any analysis, we want to split the data, because your trained data should be used to build the model. Your test data should be used for testing. But please remember, your test data and trained data must have the same columns, same number of columns, same names. Test, you don't need to really explore the test data because that is an external data. We have not seen that data. We assume that we have not seen the data, and we'll test the model on the test data. So we use library CA tools to split the data. Set.seed, we have taken as 1000, you can take it as 100, you can take it as 200, you can take it as 2. The set.seed is just a name given to store the type of split over here we are doing. For instance, in this one, we are splitting the data into 70:30 ratio, so that the R remembers the samples it picks under 70 and 30. If we change it to 60 and 40, and we want to recall this split, we can use another number. Let's say we take any random number. So this is the function of set.seed, and we split the data using the library CA tools. Because it is just 70% of the trained data that we are taking, is that the split is true, and for 30% we are saying the split is false. So this 70:30. We look at the structure of the data, which is split data. We have 642 observations in the trained data, but the variables of course remain same. We see the test data. It has 482 observations with 7 variables. Now let us test the assumptions. The first assumption we discussed yesterday was independence of observation, which is autocorrelation. In a linear regression, we have multiple variables. The data is supposed to be in random. You don't need to have in time series. So ideally there should be no autocorrelation. In order to test this, we use the test Durbin-Watson test with the library card. And we see that the data has autocorrelation is 0.02. So this assumption fails over here. The second assumption, the data should be independent. Your predictor should be independent. How do we check this? We check with a test called VIF, variance inflation factor. We first build a normal model and then we use this test VIF and we see that there is multicollinearity. A cause offered is 36. Ideally, the VIF should be less than 5, which is the acceptable level for VIF or multicollinearity. Here, IVR resolution, cause offered, even call answer is still okay, is at 5.5. But there is multicollinearity, and we will see this through a correlation matrix. Now we'll see the normal distribution test. We run a Shapiro test and it says that it fails because the p-value is less than 0.05. We have another test called case test. We'll discuss these differences maybe in stage 2. Here also it fails. We have another test with a library called NOT test, and that is the Anderson-Darling test. So there are different tests to check the normality, but each test has its own significance. But most popular one is Shapiro test, and you can go with the Shapiro test to check your normality. So here we see that the normality of data fails through all these 3 tests. Now let's check if the equation will be linear. If you run this model, we look at the coefficients, we can see that your equation is linear. So this test definitely passes, and we will see this as we proceed. The homogeneity of variance with the library card, we use the Levin test. And when you use Levin test, it takes your continuous data as your y and your categorical data as your x. So we use the Levin test for team leaders. We see it passes. We fail to reject the null hypothesis. It is more than 0.05. But if you look at the Levin test for the service level year-wise, you can see that there's a significant difference year-wise in achieving the service level. So we reject the null hypothesis over here because it is less than 0.05. So we have to investigate all the assumptions. In this analysis or the academic analysis we are doing, we will move with the data despite failing the assumptions. Because in order to validate the assumptions, in order to work on the data to pass all the assumptions, there will be several activities we need to perform, which we will discuss. But we are moving with analysis even if the assumptions fail. But I will tell you the treatment which you need to do in order to pass these assumptions. So let's look at the summary of the train data. Now we are working on the train data. Let's look at the summary of the train data. When we look at the summary, we can see for the overall service level, the minimum is 0.24, the maximum is 0.99. This clearly shows that there are possible outliers. Your median is 90, first quartile 82, mean 86. The dispersion above and below the median is not much. It means there are outliers. This note clearly indicates that there are outliers on the minimum side and could be some at the maximum side, because your mean is lower than your median. It means your mean is on the left hand side of the median. It means your data is skewed to the left, and this clearly indicates the outliers are somewhere on the lower side towards the minimum side. This is a very clear indication. Similarly, we can look at the summary of all the other variables. That gives you a visualization of data, how your data looks like, and what treatments are expected. So, in case you want to plot the model, let's run some of the libraries. These are common libraries which you would require to visualize the data and analyze the data. So let's see the correlation metrics. And we had seen, when we are talking about the multicollinearity, you can see call answered has a strong correlation. Your overall service level, which is the Y, this, if you look at this, 40% minus 0.38, what is this? IVR, offer to IVR versus call offered, it has a correlation of 85%, as a positive correlation. This is a negative correlation of minus 0.86, that 86%. Call offered and call offered to IVR also has a strong positive correlation. But if you look at your correlation with overall service level, we'll see that it looks like all the predictors are strongly correlated with your overall service level. At the same time, there is multicollinearity, which we saw even from the VIF test. Now, based on this, let's look at this, let's visualize this graphically by creating a scatter plot. This is the graphical portion of your correlation matrix, and you can validate the number, the direction from this graph. This again, and there's a mirror image which you can see. You might see the different directions. So these are some of the exploration which you must do to visualize your data or to understand what your data looks like. You can also look at the box plot to validate the outliers. So you see, IVR offered to IVR per month, this has the maximum variance. If you look at the service level, it's all, now you can see 0 and the other numbers, because these variables, they are under different units. That is why you will see, since this is in percentage, IVR resolution, this is in percentage, these are in numbers. That's the reason you will see the placement is quite different. But this is just to see about the outliers, and you can see the outliers. If you talk with the overall service level, you're not seeing outliers on the upper side, which we will see with the data or statistically. The next step is just to have a look at a histogram of the overall service level. And you can see that your data is skewed on the left, and which we will see with the data and when we build up the model. Why the model? If the model is good and the model is not good, if not good, what can be done about this? You can also explore using the explore function, and this gives you a very clear picture if you want to analyze all the variables with one another. So if I take the overall service level with the team leaders, you can see the differences, but if you see, there's no significant difference among the performance of the team leaders. Similarly, if I talk about the calls offered with the overall service level, you can see very clearly that your service level, when your call offered is between 80,000 to 120,000, the service level is above 80. Or as it moves beyond 120, the service level drops. When it is around 200,000, it is getting better. Maybe because in one of the years you have increased the manpower. There could be different reasons why over here it is good, certainly it drops, and again at 200,000 your service level is better. Maybe you have improved the resources. There could be different reasons why. So we are not looking at the reasons right now, we're looking at the graph or the performance. We can also look at you can also explore the data using the Data Explorer, which is a very powerful report. It gives you several analysis or visualization of data for the univariate, multivariate, and you can use this for your analysis for your EDA. It takes time, and that's the reason you see this say stop. It's working the back end. Sometimes if you really want to stop, you can interrupt R. We must also check the missing values, which we have discussed earlier. There's no missing value in this data set. With the library lanyard, you can see the graphical presentation of the missing data set. You can also find the outliers. You can use one or two libraries, the tidyverse, and we check the outliers using these codes. When we calculate the outliers, the formula is very simple, which we have discussed earlier. It is for the lower end of the outliers. You take the Q1 minus, you take this 1.5, which is a shift, which is a natural shift wear and tear in any process, into the IQR. For the upper side, you take the Q3 plus 1 plus 1.5 into the IQR. Let's calculate the outliers. Let's see the outliers in the data. Lower limit, upper limit. We print the outliers. So it says, this one, if you look at this, it says below the quartile 1, any data value below 63% is an outlier. If you look at the upper limit, It says that any data value above 115% service level is an outlier, which we don't have in our data set. We can print the outliers. We can print the outliers of the service level, and we can also count the outliers. There are 12 outliers which we have calculated. We can also plot the outliers, and you can see the positions of the outliers, which you can remove if you want. If you want to treat your data, you can remove the outliers. At the same time, if you think your business cannot remove so many outliers, you can also cap the data, cap your outliers at 95% and 5%. Keep the lower limit below 5 percentile and the upper limit at 95 percentile. And you can calculate your outliers. Instead of 25, I've taken 5%. Instead of 75, I've taken 95%. And we can calculate the outliers. So here, anything below 5% or 5 percentile, your 41 and below is the outlier. On the upper side, anything above 117% service level is an outlier. What happens? Does the outlier count change? From 12, it has come to 8. So accordingly, you can adjust the outliers. The calculation and the capping of the outlier can be done according to the business. In case you want to remove these outliers, this is the code. You can remove them. But in this case, when we are training you, we are not removing the outliers. We are leaving it to you because the outliers cannot be removed based on statistical inferences. It can be removed only based on the business. So let's start building the model. This is the first model we are building. This is LM is the linear model. Overall service level, and this is the formula sign. We give a dot and a comma. It means it's taking all the other variables. When you give a dot and a comma, it takes all the other variables of your, let's see, from the data. This is your data from service train. It takes all these predictors from your data set. When you give this formula sign, dot, and you put a comma, and this is the data is equal to service level train. And we run the model, and we see the summary of the model. And this is what we discussed yesterday. We taught you how to interpret the estimate, the intercept, the standard error, and the t-value. In case you did not understand, please go back to the video uploaded yesterday, and you'll be in a position to understand this. Because this is the most important part of the analysis. You must understand to read and interpret the outcome of a linear regression. Here the R square is 74.9, adjusted R square is 74.5, not much difference. And overall this model looks good because the p-value of the f-stat is less than 0.05. It means we reject the null hypothesis. Null hypothesis says that all the coefficients are 0. Alternate says that one of the coefficient is non-zero. So when we reject the null hypothesis, we are assuming that one of the coefficient is non-zero. It's not 0. So we can see all the coefficients are more than 0. And we can see we are not seeing any significant value signs over here because these are factors, categoricals. Whereas these ones, 2009 is significantly affecting the service level. 2020 is affecting the service level. Leaders, team leaders are not affecting the service level. They are performing at a similar level. 2018 did not really have a significant impact on the service level. Maybe the process was new, maybe the people were enough. There could be different reasons. We are not getting into the reasons. So this is the interpretation of your model. Now we will look at we have looked at the VIF, and we had seen the call offered had the highest VIF. What happens if we remove this from the model? We want to remove this from the model. Now what happens when you have to remove this? We have to repeatedly write everything. So what we do, there's one code called alias, and we take the model with alias and it gives you the names of all your variables. So you can just copy paste from here. So from here we have removed the calls which had the highest calls offered. So we have removed the call answered. We have removed the call answered from here, and we just want to check what happens if we remove the call answered from the model. What is the impact? So we have named this as model 2, and we see that the R square or the adjusted R square had moved from 73. The earlier we had 74%, 74.5. Now it has dropped. It has dropped to 55.5. There is a significant dip after removing the calls offered. It means call offered is a very significant factor for the service level. At the same time, it is correlated with some other predictors. So if the R square drops, this does not mean that your model, what you're building is wrong, or what you're building is incorrect. R square does not impact the model. Your model may be good. The accuracy or the objective of building the model may not be met. So in order to improve the accuracy of the adjusted R square, what we need to do, we need to treat the data because we have several outliers. Then we need to treat the outliers in order to improve this R square. But whatever, according to the significance, what we are seeing from the model, whatever prediction that we may get may not be wrong. You cannot say that your model is wrong. Maybe you need some treatment, your data needs some treatment to improve the R square, to improve the accuracy of the model. So we will now predict the model. What is the objective? The objective is to build an equation. So what is the equation? Predicted y, we are trying to predict something. So what's the formula? Intercept plus beta 1. Beta 1 means one of your variable, the first variable, into x. Let's say one of your variable is I'm taking this as offer to IVR, and one of the IVR data which comes to you is around 2000 calls. So beta 1 into x data value into the x data value. Let's say I'm just showing you practically. IVR offer to IVR. So let's say I'm taking this particular value and putting in the equation. I'm taking only this particular value. Then for the second beta, we take this particular value. For calls offered, we take this particular value. For the call answered, we take this particular value, and we are trying to predict the service level from this equation. And this is what it says. The coefficient, we pick the coefficient from here, from your model. We pick the coefficient from here, which is this, and we multiply with the x value, the data value which you want to use. And this is what you have to substitute, which we will see in another video. Now we want to predict. We have built the model using trained data. Now we will predict using the test data. This is my model which we have built, model 1. We are working on model 1 because we are assuming that we are not removing any variable. Let's work on model 1. Similarly, you can predict for model 2, you can predict for model 3. It's all trial, hit and trial. Keep on building different models, keep on removing the models, keep on adding the variables, keep on trying. It might give you a different R square and you might go with a different prediction, different model. So it all depends what type of model you are looking for. So if we are trying to predict, we use the function called predict. We save it another object and predict the model which we had built, model 1, and this is my test data. I'm predicting on the test data. We say run and let's plot this. We want to see both together. What are we seeing? This is my predicted value here in the blue. In the blue is my predicted value. In the red, it is my original test data of service level. And you can see most of the data points are very close to each other, except at the lower end, where we have a lot of outliers. When you have outliers, prediction becomes tough. And this is what we can see. But see, if you see overall, if you remove this part, your model is good. It means the treatment which you need to give to your data is to remove the outliers. If you remove the outliers, you'll get a good prediction. This is what you can see, that you cannot distinguish between the red and blue. So we will see this train model on Excel sheet. We pick the data from here using this code and we pick the train data and the best fitted value. What we are trying to see, we'll see the predicted value from the train data. Please remember, I want to see the predicted value, this code, I want to see the predicted value from the train data, from the model, and I want to compare that how the fitted value performs against the original train data overall service level values. Let's see. If you see this, there's a model predicted and there's a train data original. I take the error, that is this minus this, I take the error, I square the error. Once I square all the errors, we take the sum of this difference or the error. Then we take the mean of this sum square. And then we had squared it over here, we are putting a square root. That is the root mean sum square error. So it shows me 0.06, which is 6%. My error, let's understand this. My error, when I built a training model, and I'm testing within the training model itself between my original data and the fitted value or the predicted value from the model, it gives me an error of 6%. This gives me an error of 6%. Now I want to build a model. Once I have built the model, I want to predict on my test data and I want to see the error. If the error is quite similar to each other, it means your model is good to go. Even though your R square may be low because you need some treatment in the data, but your model may be good to go. So if you look at this now, the fit value, and I want to see now, this is my predicted, which I predicted on my test data, and this is my test original data. This is a data which nobody sees. This is an external data. Your client will not show you this data. They want to see that the model which you have built over here, does it work on their test data or not. If that works, it means you are good at your skill. So this is the predicted value with the test data. This is my original. This is my error. Same calculation what we have done over here. Sum square of difference, sum square, mean of the sum square, and this is my RMC. Now see the difference. Here also we are getting around 6%. Here also we are getting around 6%. What does this mean? It means this model is actually working on the test data. This model is working well on the test data. It's working well on your test data. Please remember one thing. This is working on a test data because the entire data which was stripped has the same pattern. Now, many a time when your client gives you a test data, it may not have the similar pattern. It may be totally different. In that case, you have to work very hard on the treatment of your trained data, because whatever you're doing on your trained data, it applies the same mechanism on the test data. If you're trying to remove the outliers from your trained data, if you're putting only 3 predictors in your trained data, when the test data comes in, the model will remove those predictors which you have removed. If you have 3 predictors in your trained data model, when the test data comes in, it will remove, or it will only keep 3 variables from the test data and remove the other variables. And that's how your model works. So it requires a lot of hits and trial. It requires a lot of understanding of the business. And only thing we suggest is to try different models, remove this variable, add another one, and keep an eye on the R square, adjusted R square, and also keep an eye on this RMSE over here. You can calculate this very easily on R itself. There are codes which will give you all the measures of the models. But I have done this to make it easier, just to show you how it works on Excel, so that you can dirty your own hands and you can find the errors and how you can find the measures, and you must see how this, what is the objective, what is the goal. Your goal is to minimize this RMSE. Your goal is to minimize this, and practically if you see, your goal is to bring all these scattered data close to the line. All these blue points should be going along with the straight line. It means you are trying to straighten the line for a better prediction. You're trying to make it a straight line. So you have to minimize the errors. Once you minimize the errors, you'll get a better prediction. Okay, so thank you so much for your time, and we'll discuss another chapter, another topic in our next video. At the same time, you're welcome to connect with us on +91, that is India, +91 7838 258 258, or you can write to us at info@abscanalytics.com, and you can also connect with us by WhatsApp on the same number, +91 7838 258 258. Thank you so much for your time, and have a good day.